kind of going over polynomials. I was going to give a little surprise pop quiz. I know, right? That would have been good. But lucky for you, I didn't get to make it this morning. Or print it. Yeah, right. I mean, I could still give it. I could just pass out a little piece of paper and write a few things down. No, that's okay. So the first thing, a polynomial. You were asked to read section 5.2, and that's why I was going to give you a little pop quiz. Sometimes when I ask you to read, I want to see, did you really read? But again, alas, I don't have anything copied. So, what is a polynomial? Does anybody know? Nina. See, you would have done well in the quiz. A monomial. So a monomial is just a term. 3x squared. One term is a monomial. Or sum of monomials, so now I'm adding a couple of them together. There's one special thing about the monomials and their exponents. Does anybody know what has to happen with all the exponents of a polynomial?
They have to decrease.
They have to decrease. What else has to happen with the exponents? It has to be a special type of number. Let me choose. Excellent. Oh, I cannot spell. Let me, pretty sure she said part 4. Let me ask. I know she's not coming in second. Yeah. I mean, I could have written wrong numbers down. But I know she has worksheets on the side of her classroom. Sorry. Alright, so monomial or sum of monomials whose exponents are positive, and then Nick said they descend, and they're going to descend in order. So if you saw in your book, a polynomial has a crazy form to it. So f of x, remember that means we're talking about a function. And it's a whole bunch of powers, really. And those powers descend in order. And in your book, the notation they give you for a polynomial is similar to this. So it starts out with the largest exponent. The number in front is just a coefficient that corresponds. Maybe it's a 5, maybe it's a 7, maybe it's a -3. And then to show something descends in order, we subtract a 1 from that exponent. So if my exponent was 5, the one after it should be 4. And to show that kind of in an algebra format, we say n minus 1. So whatever the first one was, 1 less power. And then we continue that pattern. Now I have 2 less from where I started. The coefficient in front also gets that notation just to show that they are attached together. And then there's a little plus, and this goes on, and I'm out of space because I wrote too big, forever, until I run out of powers. So the little 3 dots just means it continues. And then it ends with the last power of 1, and then just the last term of a sub 0. And then underneath this, we'll talk about what these mean. But that's the form of a polynomial, like the definition, the algebraic definition instead of the wording. That's what a form of a polynomial looks like. It looks kind of weird. So the key thing is that you have positive exponents. Those exponents descend in order. If it has a negative exponent, it's not a polynomial. If it has any other kind of exponent, if it's not a whole number, positive, and maybe we should say whole number. So they can't be fractions either. Then it's not a polynomial. If it's a decimal as an exponent, it's not a polynomial. So underneath that, I added an extra piece here, but just kind of explain what these mean. So the n is called the degree of the polynomial. And the degree is just the largest power. So whatever the largest power is called the degree. So I don't just say, oh, what's the largest power? We have a fancy name for it. It's called the degree of the polynomial. So if it's a 5, then the degree is a 5. So whatever the largest power is. A sub n is called the leading coefficient. So we have all these fancy names. So the leading coefficient is the number attached with that largest power. So if my largest power was a 5 and I had a 4 in front of it, 4 is the leading coefficient, the number in front of the largest power. And then the last part that I added, because I don't think you have this there, a sub 0 is the constant number at the end. Remember, a constant is just the number by itself without a variable. That should be the last thing, if there is one in the problem. It should end with a +1 or a -5, a +6. So polynomial has a couple parts. We're going to look at a couple of common polynomials that we have worked with so far. And then we're going to see if we can identify polynomials as well. So what makes a polynomial, what wouldn't be a polynomial. Any questions so far? So everything that we've worked with the factoring, with combining like terms, with foiling, all of those have been polynomials. So all those powers are polynomials, equations with powers. So examples of polynomials versus ones that wouldn't be polynomials. Can anybody give me an example of a polynomial? So think kind of what the definition says. Nick, what do you think?
Pi equals x squared minus 2x minus 1.
Yeah. So polynomial. Powers descend. We start with a power of 2, and then we just have an x, which really has a power of 1, and then it ends in a number. So that's a polynomial. How about another example of a polynomial, Chris? So you can think of anything, as long as the powers are whole numbers and positive, they descend in order, it's a polynomial. Something that wouldn't be a polynomial. So on the other side, sometimes we can have equations that actually have an x as an exponent. We're going to look at those later on, chapter 6 and chapter 7. Those are not polynomials. The exponent could be anything if it's an x. We might have something that has 3x maybe 2 1/2. And then maybe plus 2. That exponent is 1/2, not a polynomial. Or maybe I would have 3x, I must like the number 3 today, maybe to the negative 2 minus 3x to the negative 1. That would also not be a polynomial. So anything that you can think of where the exponent is not a positive whole number, which whole numbers actually are positive.
And if you move the two negative exponents down to the bottom,
Yep.
would it be a polynomial?
Nope, because now it's on the bottom. So once it's in the denominator, it's a different type of function. Other questions? That's chapter 8. So we'll get to those.
Since like it wouldn't work as a fraction there as well, would it also not work for a decimal?
Yes, yep. And yeah, so if it was a decimal, so we could say 3 to the point 2, 4, 5, 7. I missed my x, but whatever you want to put up there. Any kind of decimal.
What if it was a decimal? Like, what if it was 0.3?
Nope. Other questions? So the exponent has to be whole numbers. Dimitri.
If the exponents are out of order, can you rearrange
Yes,
them?
yes, exactly. You'll be asked to do that. If the exponents are out of order, that's okay. We would rearrange them and get them in order. So as long as the exponents are positive whole numbers. If they're not in order, we'll rearrange them in order. So there is a list of common polynomials, and I'm going to use the form f of x for these. So if it's a constant, that's just a number. So f of x equals a sub 0. So any number, like f of x equals 7, is called our constant function. What type of graph makes a constant function? Say y equals 7 or f of x equals 7. Peter, what's that graph look like? It is a line, just a horizontal straight line. So that's what a constant equation is. It's not changing, it's not moving, your line is constant. The slope is constant because it's 0. So then if I build on that, my linear equation, we usually think of it as mx plus b. I'm just going to put an a there to kind of see how these pieces can build on top of each other. So that constant, now if it goes in front of x, now I have a line, and we've worked with lines in 1 through 3, so maybe x minus 7 now is my line. In chapter 4, we worked with quadratic functions. What's the standard form of a quadratic function? Jack, do you know what the standard form of a quadratic function is? So notice how the a and the b from the linear form is still in here, but as I add a power of x, we also get an extra constant at the end. So you can see how one equation builds on the previous. And that's really how algebra works. So it starts basic, and then each thing you just build on what you have. So again, if you want to write yourself an example, you can. You don't have to. 3x squared plus 2x, maybe minus 1. Whatever you want to write back there. So what would a cubic equation look like? Peter, what would a cubic equation look like? Plus d. So every time we add a power, we get an extra letter or number in the end. Each one of those letters, A, B, C, D, they're just constants. They're coefficients. They're numbers that are attached to our powers. What's a quartic? Jack? Yeah, an exponent to the power of 4 is called a quartic. So ax to the 4th, bx cubed, cx squared, dx, and then plus e. That would be a quartic. After that, they don't really get any special names. Kind of run run out of names and we just say a power of 5 or a function to the 5th power. But these would be the common ones that we will see. So underneath, I think there are 4 examples, and you are asked to decide if it's a polynomial. Is there 4 or just 2? Yep, 4. If it is a polynomial, write it in standard form. State its degree, the type, and the leading coefficients. That's a lot of information. Let's start with the first one. Is it a polynomial? Yes. Okay, so it is a polynomial. Looking at the powers, there's a 4, there's a 2, and then that plus 3 is constant. So this is a polynomial. The second part, is it in standard form? So do the powers descend in order? Yes. So it already is in standard form. We don't really have to rewrite it. It's okay that it skips powers. I don't have to have all of the powers represented. They just have to descend in order for the ones that are in the problem. So it is in order as it was written. Part 3. What is the degree? So looking above, kind of seeing what the degree means. And then leading coefficient. So what's the degree of this polynomial, Jack? A 4. The degree is the largest power. So the largest power is a 4. So Jack, what is the type? A quartic. So he says a quartic, and then the last question, Jack, the leading coefficient. Yeah, and why is it 1? Right. So the leading coefficient is the number in front of the highest power, and it's just a 1. Questions? All right, let's look at number 2, or letter B, I suppose. Is this a polynomial? Yeah. Yeah. So the powers of the x's. This has a power of 1, that has a power of 2. It's okay that it's a square root of 3. That's a number. It's not an exponent. So this is a polynomial. Nick, is it in standard form?
No.
How would you rewrite it so it's in standard form?
IX squared plus 7x minus square root of 3.
Great. Again, it's okay there's a pi in there too. It's not an exponent. Nick, the degree is?
2.
The type would be?
Quadratic.
Good. And then the leading coefficient. Excellent. See if we can do the other 2. So is it a polynomial? Look at the powers. That's what we're focusing on with polynomials. What are the powers? Then you don't have to do anything because it's not a polynomial. So if you say no, then you don't have to do anything. It's not a polynomial. So Cole, what would you say about C?
I said it's not a polynomial.
Because?
There's a negative
Right. There's a negative
exponent.
exponent. It's not a polynomial. Nina, how about D?
No.
Why not?
Because it has x as the
Yeah, it has x as the exponent. That's actually called an exponential function because the x is the exponent. So both of those are no. Questions? So at the top of the next page, just as a little review here, state the degree, the leading coefficient, the type. Maybe put it in order if it's not in order. Ava, is that in standard form?
Yeah.
So if we wanted to write it in standard form, what would it look like?
Negative 3x minus 2x cubed plus 2x squared plus 5.
So then the degree is the type and then the leading coefficient. Questions? The leading coefficient is always with the largest power. It doesn't matter that it's not first here. Once you write that largest power first, it's the part that comes in the front. So it's called the leading coefficient. It should be the first thing that you see in the function. So the other things that we're going to talk about underneath are trying to start interpreting graphs. And you're going to really be looking at kind of investigating this tomorrow. It sounds scientific when I say investigate. So the first thing here, it says, what is end behavior? Does anybody know what end behavior is? Josh?
Something reaches infinity.
Yeah.
What is it?
So generally when we graph, we're so focused on what's happening in this like middle of the graph. When we were doing parabolas, we were looking for x-intercepts, we were looking for y-intercepts, we were looking for the vertex. You don't really focus on where it ends because most graphs just go on to infinity or negative infinity. But sometimes the end behavior can be determined just by looking at the equation. And what about the equation tells us information about the graph? So parabolas, we know they open up or they go down based off of the number in front. We're going to look at the end behavior, and there are 4 different options for end behavior. And there's a little chart here. And I'm going to try and make this chart seem a little easier, a different way to kind of think about it. But end behavior is like, where does the graph go to infinity? A graph has 2 sides. It has a left side and a right side because it has the negative x-axis, it has a positive x-axis. So in the little pictures here, there are 4 different options. The first 2 have odd degrees. So now because we're dealing with all polynomials, we have to first look at that leading coefficient and the largest power and think, is it an odd or an even? Because that creates a different graph if I have an odd power or an even power. And there are only 2 types of numbers, so really there are only 2 options that we have to choose from. Except, besides the degree being odd, the leading coefficient can be positive or it can be negative. And that's why I give 4 cases. So, again, I either have an odd power or an even power, but then the coefficient could be positive or negative. And those 2 things force the graph to go a certain way. So for odd, think of a graph that would be like 1x cubed, or 3x cubed, or 5x cubed. So this notation is going to seem a little weird, but I'm going to show you an easier way to think about it. But the actual algebraic notation, so it says as x, this little arrow here means goes to, approaches. So that little arrow approaches or goes to. So as x goes to infinity, that means I'm on the right side of my graph. F of x, or if you like to think of it as y, because sometimes y is easier to think of than f of x, also goes to infinity. So if I look at my end behavior, that's the part where the graph ends. Well, it's going to infinity on the right side of the graph. An easier way of thinking about this is saying the right side of the graph goes up. So my end behavior on the right side is going up. That happens every time I have a positive odd power. So 3x to the 5th, 3x to the 7th, 3x to the 21st. Positive number in front and an odd power. On the other side, as x goes to negative infinity, now I'm on the left side of the graph, the y goes to negative infinity. Or I could say the left side goes down. And again, we're focused on the end. So the left side is going down, the right side is going up. So an odd graph splits. So half of its graph goes down, the other half goes up. It's a graph that splits in half. It doesn't decide what it wants to do, so it does both. So if you can think of it as the sides of the graph and what each side of the graph does, that's really what end behavior is. What is the left side doing? What is the right side doing? So if you look at the one right next to it, because the power is odd, but the number in front is negative, it forces the graph to do the opposite, which I know if I had a graph that had a positive number in front and then a negative, it's going to decrease instead of increase. So my graph does the opposite. So if I look here, the end behavior, now on the left, it's going up. Whereas on the other side, it was going down. So as x is on the left at negative infinity, the y is now going up to positive infinity. So again, like this is the algebraic notation, but think of it as the left is going up. It's way easier to think about. The left side goes up. On the right side, now it's doing the opposite. The right side is going down. Or I could say the y is going to negative infinity as we're on the positive x-axis. So here's the algebraic notation to think the right is going down, the left is going up. So by looking at an equation, if it has an odd power, I have one of these two cases. So part of your homework tonight is just looking at the equation and saying it's going up or down on the left or the right. The other two cases are when the power is even, because again, we only have two types of numbers. It's either even or odd. And the leading coefficient being positive versus negative. So the graph that you see here is an example of a quartic graph. And notice with even powers, they're going to do the same. So even powers, they either both go up together or they both go down together. And that was our parabolas. X squared is an even power. The parabola had both go up or it had both go down. So looking at the fancy algebraic notation, y goes to positive infinity on the left side, or we could just say the left side goes up. Y still goes to positive infinity on the right side, or we could say the right side goes up. So end behavior is describing the two sides of the graph, thinking of it as a left and a right side. What's happening with the left and the right side? So then the last option here, if it's a negative coefficient, instead of it going up, it's flipping and going down. So the y goes to negative infinity on the left side, and it also goes to negative infinity on the right side. So when you're asked to describe the end behavior, left versus right, where's the graph going? Is it an even exponent or is it an odd exponent? Is it positive or is it negative? So I'm going to skip the little definition for now. We'll talk more about those later. We're going to see if we can graph this function. But before we graph it, I want you to just describe the end behavior. So to describe the end behavior, you need to find the degree and the leading coefficient. So I just circled that largest one, negative x cubed. So the power is odd. The number in front is negative. I'm I'm checking the end behavior first before we even go to think about graphing it. So can anybody just tell me what should happen on the left and the right because it's odd and negative? Chris. So because the power is odd and there's a negative in front, that's this option up here on the right side. The left should go up and the right side should go down. So now we're going to see if we can graph that, and that should be where our graph goes. The left side should go up, the right side should go down. So the directions want you to make a table of values and plot the corresponding points. It says connect the points with a smooth curve. Polynomials are very curvy. They're going to have a couple of hills and valleys depending on the power. So we should see smooth curves in our graph. So making a table of values. What would be some good numbers to pick for a table of values? Nina, what do you think?
0, 0.
All right, so 0 is a good one to pick. What other numbers would be good to pick? Sadie, what else?
2, 1, -2.
Yeah, those are usually good 5 numbers. So we're going to plug them into the equation. If you'd like to use your calculator, you can. So you're going to plug them in for all of the x's and get out the corresponding y values. So you have a -2 cubed, a -2 squared, 3 times -2, and then -3. Make sure that extra negative, that should be outside. So you have a negative and then in parentheses, a -2 cubed. Make sure you're placing the number, entering the number in the calculator. Place that in parentheses when you enter it. Bless you. So that's what it should look like when you place it in your calculator. Then you should have 5 y values. Anybody get a number for -2? Nick, what'd you get?
3.
Yeah, I got 3 too. So the first one is -8, but then you also have a negative, so that makes it a +8. +4, -6, -3. Anyone have a value for -1? Josh, what do you have? You said -4, right? And then when you plug in 0, x is 0, x is 0, x is 0. There's just a -3 there. That's the only number that's there. All the x's are 0. That's why it's really good to use 0. Plugging in a +1 gives us -1 plus 1 plus -3 minus 3. Jack, what do you get when you plug in a 1?
0.
A 0. And then the last one, what do you have when you plug in a 2? Did anybody get that far? Jack, what do you have there? -1. So you have 5 problems that you'll be graphing tonight. I ask that you make a T-chart with your graphs, and I'll get your graph paper in a minute. So we're going to plot these points at -2 going up to 3. -1 is down to 4. And then 0, -3, 1, 0, 2, -1. So we're going to play connect the dots. I start on the left side when I graph. And I am connecting the dots. So it starts up at +3. It goes all the way down to -4. So if I connect the dots, And then at -4, just plain connect the dots, my next point has to go up. Make it curved as best as you can at the bottom to connect it up to the next point. Again, just plain connect the dots. I have a point at 1, 0. It has to curve to continue to connect the dots. Now we only picked 5 points, but I know that it has to go beyond that. And we also know that the left side should end up. So if I go to that left point, just make it continue up. Go to the right point, make it continue down. The last question is about domain and range, which we haven't talked about in a while. The domain is how far it stretches to the left and to the right. How far is this going to stretch to the left and to the right? There? Infinity. So our domain would go to both infinities, negative infinity, positive infinity. It stretches forever to the left and the right. The range are the y values. How high does it stretch to the bottom and the top, Jack? Great. Negative infinity to infinity. We'll talk more about that again. It was chapter 2 when we talked about that. We'll be going over that and starting to look at those again with these new graphs that we'll be analyzing. So again, your homework tonight, you'll be asked to kind of talk about end behavior. You'll be asked to decide if something is a polynomial. And then there are 5 graphs, the last 5 problems. Please make sure you have a T-chart. You connect them with smooth curves. Try and get them to be curved as you play connect the dots. Have a fantastic day.